Oh boy, today's gonna be a little bit of review on stoichiometry, of course, but we're gonna do redox stoichiometry. But we're gonna do a little review with how to get equations and things like that too. Some things that we haven't done for a little while here. So this is all gonna be fun, and we might even go, might see some explosions today. And we won't be in the chem lab like we are tomorrow, by the way. Don't miss tomorrow, because tomorrow's lab will take basically the entire period, guaranteed. Okay, so don't miss tomorrow. If you miss that one, I'm going to tell you right now, don't make any plans for a week, because it's going to take you that long to catch up. You can use a balanced redox reaction or equations to compare chemical amounts. Remember, there's two ways of doing that. There is little m over big M. There is C equals N over V, of course, N equals C times V. There's also a gas one, by the way. Remember, PV equals nRT from Chem 20. It's been a little while for some of you, but there is one there as well. We're not going to worry about that one. But these are some of the more common ways that we're going to talk about with Chem 30 here. This first one here, calculate the volume of acidified 0.225 molar potassium dichromate need to completely oxidize 5 grams of aluminum. Well, probably the first thing you need to do here is come up with a balanced chemical equation for this, okay? In order for that to happen, you have to look at this and say, what's my balanced chemical equation? Yes? And you're going to do what to get that? Somebody help me out here. Huh? Yes, you are. And how are you going to do it? What do you need to do? To do that word problem there. Write down everything you have. So go ahead and do that. Start. Go. All right. So listen. I love this question, because this one, if you really understand this is all the stuff you need here, right? First one. What do you think's the first thing? Huh? Why? It says acidified. So let's put down some H+. Good. What else? Water. Why'd you pick water? Oh, it doesn't say solution here anywhere.
It's an acid and it's concentration.
Right, exactly. So that's exactly what you need to be careful of, things like that. So water, because it gives you a concentration. So we're talking about moles per liter. Right, I don't know if it's liters or not. In fact, it's not. Okay, that's part of it, but it doesn't matter. They're talking about moles per liter, a concentration. So they're talking about a solution, even though they don't say it. And how else do you get H+ if you don't have water, right? You need to get H+. You need to have water to have H+, correct? Because water is what's going to break that acid apart. So that's very important. Good. So since you have water, what else do you have? What else? K+, potassium dichromate, correct? So you're going to make a list of all those things. And what else do you have? Last thing here. A solid chunk of aluminum, yes? And 5 grams of aluminum. Perfect. Okay? Now, that's your list. And that's the list you should have. And if you don't have that, be very, very careful. Yes, you may still get the right answer, but I'm not going to guarantee it, okay? Because all you have to do is switch a few things here, and then, of course, you will get the wrong redox reaction, and it's not going to work out. So you're going to look up in your data booklet, right? SOA, SRA. Ooh, looks like this one here. SOA, yes? So we're going to write down here, reduction half reaction. Looks like this. Dichromate and 14 H pluses and 6 electrons gives me 2 chromium 3 pluses and 7 waters. Okay? From the data booklet. Top left, working our way down, yes? Okay? Yep. Oxidation, therefore. Okay? Bottom right, start working your way up, and you will find aluminum, of course, is one of the first ones you're going to see there. Aluminum solid gives me aluminum 3+ and 3 electrons. Okay? So hopefully that's what you need to start with. And if not, then maybe we need to do a little bit more review on that, and then I'll leave that up to you guys. Okay, yep. What's that? That's the equation that it gives me, right? A match exactly on the left side, you mean? Yeah, it did, right here. This and this, those two. Those two gives me that, right? Top left. Those two are gaining the electrons, right? So that's my SOA. This one is losing the electrons, that's my SRA. No? We're going to add these up. Okay. Don't forget to add them up. We're going to have to take this one here and times it by 2. Balance out the electrons. Yes? So here we go. Cr2O72 minus and 14 H pluses and 2 aluminum solids gives me 2 chromium 3 pluses, 7 waters, and 2 aluminum 3 plus aqueous. Okay? So there's my final redox reaction. Good? Questions? Okay? So once again, if you, like I said, you have to be able to come up with that, because if you can't do the next part, which is, of course, the stoichiometry part, because the balancing is going to be off. In fact, if you do this first part wrong, you might not even end up with aluminum in your equation, which is kind of a problem because it says here that we need to oxidize 5 grams of aluminum. Okay? So this is now, the rest of this is Chem 20 stuff. Okay? However, I'll do this for you first here. When you were in my class, and if you're in somebody else's class, hopefully they did this as well, I don't know, but I like to line stuff up, yes? If you had 5 grams of aluminum, I would probably put that right here. You don't have to, okay? But I like to line stuff up and put it where you know it's going to go, right? And it says we have 0.225 molar potassium dichromate. Where did I put 0.225 molar potassium dichromate then? Where would I put that up here? Somewhere, anywhere, or not? What do you think? Questions? Yeah. Yeah. From the equation. I didn't. I got it out of the data booklet. That's what it says in the data booklet. Top left, working way down. Find it. 5 grams aluminum. Okay. Yeah. What about 0.225 molar? Where does it go? Huh? Nowhere? Yeah, it does. Right here is 0.225 moles per liter. Okay? Yes? Now, question. It doesn't say that here though. It says 0.225 molar potassium dichromate. Is this okay? Can I do this? Is that true? Or not? In Unit 3, Chem 20, if you take potassium dichromate and you put it into water, that is called what? Thank you. Dissociation. And you will get potassium ions and dichromate ions, correct? True? In water. Yes? This is Unit 3, called dissociation of ions. For you, 0. Okay? Yes? True? You would balance it, correct? Is that balanced now? Yes. And if I told you that I had a 0.225 molar solution of potassium dichromate, what's the concentration of the potassium ion? Same? No. Double. So 0.450 molar, yes? But what's the concentration of the dichromate ion? The same, correct? Because it's a 1-to-1 ratio, yes? So therefore the concentration would be the same. So is it okay if I put that up here? Right there? Sure it is. because the concentration is the same. Now, what else do you know about potassium in this case? Potassium ion is actually a spectator ion in this case, yes, because you'll see it's not involved in the final reaction here, right? So it's also a spectator ion, so we don't need to worry about it, okay? However, you do have to be a little bit careful here. What if they did talk about the potassium ion in this equation? Now, obviously they don't, but what if they did? Would I be able to put my 0.225 here? No, you'd have to actually take double the concentration. So you do have to understand this in case it's not a one-to-one equation, right? Having said that, I would be shockingly surprised if you ever came across that question. I would say 95% of the time you would not have to worry about that. There always could be a 5% chance. I'm not going to rule it out. If they did that on the diploma, I'd be surprised. However, you do have to understand that that is the case. What is happening there? Okay? We do expect you to know that. So, just keep that in mind. All right? We're going to get rid of this because it turns out for us the 0.225 molar potassium dichromate is the 0.225 molar dichromate ion concentration. So what else do I need here? It says calculate the volume of this. Okay? So what else do I have? Well, let's see. Stoichiometry. Molar mass, 26.98 grams per mole. I can find N, right? N works out to be 0.185-ish, etc. moles. I'm going to move that over to here. Now, do you remember stoichiometry? Yay! 2 to 1, right? So 2 to 1 reaction here, divide by 2. That's why that balanced chemical equation is obviously important. Divided by 2 is about 0.09-ish, 9266-ish or so moles. And I'll divide those two to give me V. And remember, to find V in this case is N over C. Obviously, you guys can worry about manipulating those appropriately, right? C equals N over V, V equals N over C, N equals C times V. Okay? Dividing those two, I think you get, help me out here, 0.412. Is that right? Final answer. Is that correct? Somebody? Double checked for me? Yes, thank you, everyone. Appreciate that. 0.412? Now. Okay? So, that would be your final answer for this. So you need 0.412 liters or 412 milliliters of this acidified dichromate solution to basically use up all the aluminum. Okay? So, that kind of gives you an idea of how we can use this with stoichiometry. It's good? Moving on? Yes? All right, we're going to give you another one here. If you're not, you know what, I'm going to leave this up here for a second. You guys look at the next one there and start working on that one. And if you need this, then I'll just leave that up there for a few more seconds here in case you need to copy anything down. Okay, now with this one here, you might be tempted just to write out an equation. Zinc plus hydrochloric acid gives me hydrogen and zinc chloride. And you may get away with that, but you really have to keep in mind, okay, in Chem 30 we talk about SRA, SOA, so we do want to write that out. And a little bit of practice as well, never hurt us, that's for sure. You know what, I'm pretty confident on this one. Zinc solid is probably here. I got one, cha-ching. Got an acid, H plus, Cl minus, water has to be there probably as well. I'd say that's all we got for this one here, yep. Strong acids break apart. Weak ones stay together. Yeah. So, looking this up here, let's see. First one I come across here is right here, SO8. Okay, the first one you're going to find, top left, working your way down, is, what is it here? 2 H pluses and 2 electrons gives me H2 gas. And then the second one I'm going to find here, SRA, oxidation. Oh, let's see, zinc solid gives me zinc 2 plus and 2 electrons. Oh, look at that. 2 and 2, so we can just simply add these up. Lost 2, gained 2, perfect. Redox. Let's see. 2 H pluses. And a zinc gives me H2 gases and zinc 2 positive. Now, once again, you'll notice, if you think back to, you know, what you would have done in Chem 20, you guys would have written out the single replacement reaction, right? Or written out the single replacement reaction. And you'll notice that probably chloride in this case was the spectator ion, right? So we didn't write that down, okay? Because it's not involved in the final reaction here. Yes? Nope, I don't think so. Zinc, I think, is way farther down there. Huh? Below what? Right below it? Are you sure? Well, we're going to go with this. Instead of... Well, let's finish this and I'll come around. Well, I'll check. That's not Cl minus. Anyway, trust me, it's this one. Okay, trust me. All right. So let's see here. Let's put down some information underneath these two here that we have. Now, it says here I have 6.50 grams of zinc. Okay. So I got that chunk there. It's placed into 0.475 molar hydrochloric acid, so obviously 0.475, and you had a volume of 300 milliliters. Okay? Look, I have C and B right there, and I can find N. But before I do this, let me ask you something here. Because obviously, could I find the molar mass and find N here as well? What kind of reaction is this? It's a Chem 20 term. Starts with L. What kind of reaction is this? It's I'm not talking about single replacement, double replacement. When you're doing stoichiometry, and I give you information about the two reactants, which I've clearly done here, you need to find out which one is the limiting reactant. True? Which is also a Chem 30 term, which we used already, right? Sure. So, which one is the limiting reactant? You can tell just by reading the question. It says, calculate the mass of zinc that's left over. Right? So obviously I have more zinc than I need. So if I have more zinc than I need, I guess this is your limiting reactant. Correct? Yes? Oh, this is going to blow your mind, this one. Hey? Now, look, if this is my limiting reactant, doesn't everything depend on this? Sure. Once this runs out, this stops, that stops, correct? Everything depends on limiting reactants. So I'm going to find C and B. I'm going to find N right here, which is, by the way, 0.1425 moles right there. Once I've used up those 0.1425 moles, I've used up all the zinc that I'm going to use up, right? So if I move this over to here, if I use all this up, which I'm going to, this is the limiting reactant. So if I use all this up, I would use 0.07125 moles here. How do I know that? Because, well, if I had 2 moles of acid, it would react with 1 mole of zinc, right? Well, I don't have 2 moles, I have 0.1425 moles, so that reacts with the 0.07125 moles here, correct? Yes? 2-to-1 ratio. Well, look, N, I can find big M, which is 65.41 grams per mole, and I can find little m in this case. So by knowing that I actually use 0.07125 moles of zinc with the molar mass, 65.41, I'll tell you it works out to be, what is that? Do I have to do that? Probably. think it works out to be about 4 something. I'm going to just double check here. 1, 2 times 65.41. Yeah, 4.66 grams was used. Okay? Because remember, in a 2-to-1 ratio, in a 2-to-1 mole ratio, 2 to 1, right? That's how much I used. I'm going to use all of these 2 up. I'm going to use all of this 1 up here, which is actually the 0.07. So that means I've used 4.66 grams used. And if I started with 6.50 grams, well, 6.50 grams is what I started with. I used that much. I guess that means I have about 1.84 grams left over. Correct? So if I had a 6.50 chunk in there, once again, okay, I used 4.66 of it. You take that out after that reaction's done, you should be able to weigh out 1.84 grams of zinc left over. Okay? Oh, limiting reactants, eh? This is fun. Yeah. All right. Yeah. Yeah.
So we think all that hydrogen is a very reactant.
Yeah.
Then molar mass of zinc doesn't matter at all.
The molar mass of zinc absolutely matters, because that's how I found, I used these 2 things here to find that.
So where's N coming from?
Well, it comes from here, because this, remember, like I just said, everything depends on the limiting reactant in this equation, right? If I had 2 moles, 1 mole would react with it, right? Well, I have 0.1425 moles here, so 0.07 moles here, right? Half as much. With the molar mass will tell me how much I actually used there. Okay? Good? Yes? If you want to talk about which ones I used there or whatever, I'll talk to you about that later here. I'll just finish this up first here, because I do want to we do have to get this done here for tomorrow. But we can talk about it at the end if we have time. All right. Next, tomorrow, we're going to go to lab. And tomorrow, we're going to talk about a titration. Titrations. Eh? Oh, yummy, yummy, yummy. Titrations. Everybody loves titrations. You guys did them in Chem 20, yes? You guys used indicators. Phenolphthalein, for example. Made it from a pinky color to a clear color, hopefully. Or vice versa if you messed it up. Yeah? So, permanganate and dichromate are 2 very commonly used titrants. And the reason they're commonly used is because, first of all, guys, they're both very strong OAs. So when you look in the top left, okay, I'll tell you right now, if you haven't figured this out already, you know, we've done a few of these with permanganate and dichromate. If you look in the top left, they're pretty high up there. They're almost always, those 2 with an acid are almost always your SOAs. I'd be surprised if they're not. I'm not going to say they're always, because there's some stuff that's higher there, okay? But generally speaking, those 2 are the highest top left that you're going to find, okay? Well, not the highest, but you know what I mean. They're up there. They're strong, okay? So these 2 with acids are very good at gaining electrons. Therefore, they're almost always your SOAs, okay? They basically react almost spontaneously with any reducing agent, of course, okay? Anything that's being oxidized. The other good thing about these 2, they have specific colors. So when you get from permanganate here, which is a purple-pink color, to the Mn2 plus ion, in other words, when that permanganate, remember, if you did oxidation numbers here, look, this is a 2 minus, yes? This would be what, a 7 plus? So look, what's happening to manganate, or manganese, it's gaining electrons, yes? So when it gains those electrons from the oxidizing, from the one that's being oxidized, or the reducing agent, it's going to turn from a purple-pink to a colorless color, okay? Right? So purple-pink to colorless, should be able to see that probably pretty nicely. And dichromate happens to be an orangey color. And if you, once again, if it gains electrons, which it would in this case here, it's being reduced. It's the SOAs, right, being reduced. So when this chromium here gains enough electrons, turns into chromium 3 plus here. I believe this, if I'm gonna think that's a 6 plus, I think, for each one is how that would work. Yeah, usually is 6 plus to 3 plus. So when it gains those 3 electrons, when that happens, it's going to change from an orange to a green color. So we don't need to use indicators in this case because the indicator is actually these parts of it. Okay, so now you guys, like I said, won't unfortunately see this color stuff on yours, but this is kind of what you're going to see here. This is your permanganate here, okay, your purple pinkish color, and it's going to turn to clear. And then this one here is your, what is that, dichromate, okay, there, and then of course turns into the chromium ion there, okay. So if you forget what titrations look like, yeah. If you forget what titrations look like, they kind of look like this right here, right? You got a burette. Whatever you put in the burette is called the titrant. Thank you. Perfect. I said that actually, but this down here is called the aliquot, is the correct term. Thank you. Aliquot. Good. Perfect. You guys are awesome. At home, people watching this at home, these guys are awesome. They got both terms right there. Awesome. Good. Aliquot. Of course, you're going to need a titrant stand, etc., etc., and you're going to mix the two together until you see those color changes. Okay. We're going to have 2 titrations for you to do tomorrow, so it's important you're on time and you're ready to go, and that you can get this done as quickly as possible. Now, here's a little chart that you guys remember from last year as well. You need to fill this in, of course. Beginning minus final, okay? Or sorry, final minus initial, I guess I should say, technically. In this case here, we do want to calculate the concentration of the permanganate, okay? So that'll be actually on the next page there. First of all, when you do titrations, I remember, if you guys remember from last year, you do on average 3, right? You do 3 at least, and then a 4th one if you need to, of course, and you most of the time you do. Okay, so you do those until you get within what? What's the magic number that you need to get all these trials together? 0.2 is the correct answer. So you need to get within 0.2 milliliters of each other, and then you do what to those numbers? Average them. So let's go ahead and do this. 15.6 here. This one here is 14.65. This one here is 14.55 and 14.60 finally. Okay? So that's part of it. If you remember in Chem 20, you guys had an equation that you guys need to write out, balance, etc., etc. Well, we have an equation for this too. This one involves ions, balancing electrons, etc., etc. A little more involved than last year, obviously. So, by the way, let's go back to here for a second. Let's average these, I guess, right? We need to find the 3, which are these 3 here, that are within 0.2 milliliters of each other, right? So, those are the 3 there. Now, remember, we might be very specific. In this case, we have 2 decimal places. Sometimes you might only have 1. It really depends on how specific you are or how accurate that measurement is, right? So I'm just going to write that down here just so you guys remember. 14.6, you're going to average 14.65, 14.55, and 14.60 divided by 3, and of course you will get 14.60 milliliters. Average. And remember, this is the titrant required, right? Obviously, on average, it's the titrant, it's the one that's in the burette. It doesn't make sense to average the bottom stuff. In fact, after the first part, you won't even remember what the bottom stuff is, right? Right? We're averaging each trial of the burette, right? The titrant. All right. Well, here's our equation. Looks a lot more complex than last year, of course, because it's Chem 30 now. So, how are we going to do this? I would suggest let's do a little oxidation numbers for balancing. Yay! There, a little review for you. Hey, we got all the stuff here, right? We don't need to come up with, I need water, I need acid, I need this and this and this. It's all there for you. You just got to balance it. So balance it. All right, go ahead, balance it. All right, so there's the oxidation numbers, of course. This one here, Mn 7 plus to 2 plus gains 5 electrons per manganese. So in total it gains 5 electrons. This, of course, gaining 5 electrons being reduced. So it's your oxidizing agent in this case. Okay. Reducing agent, this one right here, it's going through a 3 plus to a 4 plus. It's losing 1 electron per carbon. In total here, therefore, don't forget, it's actually losing 2 because don't forget there's a 2 right there, 2 carbons, right? So loses 2. We need to balance those 2 out. So we are going to say, okay, let's take this one here, times it by 5. This one here, times it by 2. And we're going to put a 2 here and a 5 here. Okay? Good so far? That's how you need to start this one. Hopefully you've done the same. Well, let's see here. 2 MNs. Let's put a 2 here. We got, what, 10 carbons. I'll put a 10 there. Now, the rest is balanced on oxygens, of course, probably next here. Let's see. I got 8 O's there and another 20, so that's 28 O's. And I got 10 there. Sorry, 20 there. And so I need another 8 O's there, 28. Okay. And let's see, hydrogen is 16, so 16 there. And that should be balanced. Okay? Good so far? Yeah? That's the hard part, I think. Now, the rest is we're going to put the information in the right spot. So, let's see. It says here that I have, what is it? 0.0227 molar. Concentration of, that's the dichromate there, I believe. No, that's the C2O4. Sorry, C2O4. That comes from the original question. So that's, if you look back at the question here, guys, I'm picking this stuff out of here. And of course, I have 10 milliliters of it as well, by the way. So I'm going to put that here as well, 10 milliliters. Right? With titrations, listen, I asked you this all the time last year, and same thing this year. What's the purpose of a titration? Yeah, to figure out the other concentration, right? So our job is, in this case, and that's what the question asks you, by the way. If you go back to here, it says right up here, calculate the concentration, square brackets, of MnO4 per manganate, right? So that's what I'm looking for here. Now, what else do I know? Well, I got C and V here. I can find N. Perfect. Okay, so that works out to be, I'm going to do this in scientific notation here, times 10 to the negative 4 moles. I'm going to move that over to here. Okay, so when I do that, of course, this is a 5 to 2 ratio, 5 to 2, so divide by 5 times it by 2 there. Divide by 5 times by 2, and I get about here 9.08 times 10 to the, what is it here, negative 4 moles. Okay. Well, gee, if I want to find the concentration, I also need to know V, right? Well, I know V because that was the purpose of the trials, right? So I know that from the other page. On average, it's 14.60 milliliters from the previous page, right? Right there. The bottom here, guys, 14.60 right there. So right here, I'm going to put in 0.01460 liters. Don't forget it has to be in liters. Okay. Now, well, yes, it does. But if you made both of them milliliters, that'd be okay as well. But don't start mixing up stuff. Basically, I always like to put in liters because that way you know. N and V gives you C, and C here should work out to be final answer, all said and done, significant digit, 6.22 times 10, I just said 22, times 10 to the, what is it, 1, 2, 3? Yeah, to the negative 3 moles per liter would be your final answer. 6.22 times 10 to the negative 3. Yeah. you'll have to do two titrations. So you're going to use one titration to figure out the concentration, and you're going to take that one and use it to figure out the other missing concentration. So you actually have two different titrations to do tomorrow. So don't be late. Be on time. And get ready to go. Okay? Questions on that? Anyone? So in this case, we used oxidation numbers, right, to balance. So kind of a little bit of review for that as well. And this, of course, is redox stoichiometry. Now listen, question, did I actually have to balance the rest of this? No, because after I got the 2 and the 5, does the other stuff really matter? No, and how do I know I got the 2 and the 5 right? Because I balanced out the electrons, right? So I'm not going to lie to you, you did extra work for this one, but I wanted you to, just for a little bit of review, of course. But if you got this on a diploma question or on a unit test, I wouldn't spend the time balancing the rest when you don't need to, okay? Now, if you don't know when you have to and when you don't, if you don't understand that, then I guess you'll be balancing the rest. That's okay. I'm just saying you could save some time because you don't technically have to in this case, okay? So after you balance the 2 and the 5 there with the MnO4 and the C2O4, you're done, okay, really. But you should know how to balance the rest, I'd hope, okay? I really hope, okay? So that's an example of that there. I got some practice questions for you because I know you're just like, oh, geez, what am I going to do? How am I going to do this? Well, I'll tell you. I got